Today's interview in today's interview we have the pleasure of having Jihn Kim, one of the most famous physicists, theoretical particle physicists and cosmologists, in connection with axion, supersymmetry, string compactifications. He was very kind to give a seminar today, and he has agreed to be our first interviewed in this series of interviews. Thank you very much for coming and for staying here with us.
Well, thank you for the invitation.
It's a real pleasure. So in this interview, we wanted to touch a couple of topics related to you as a physicist and to your subject of research. So let me just start from the beginning. Talking about your interest in physics. What do you think are your most significant contributions?
Well, people say, and I also think that I wrote a paper on invisible action. The title was Weak Interaction Singlet and Strong CP Invariance. Still the title works. Mm-hmm. And it was the maybe first time introducing singlets in addition to the standard model fields. So it was in 1979.
So in addition to inventing the axion, you also invented somehow model building, or one of the...
Yeah, I was very much interested in model building from early days. From the chaotic period of neutral current, which established the standard model, I was interested in model building, yes.
Very good. So let me just one step back and ask you, when you were a young student, what motivated you to study physics, and in particular, what motivated you to study theoretical particle physics?
Okay, so I started to do science in very early days of my life. At age 10, it was about 10th grade, I wanted to become a physicist, because in Korea was independent from Japan because of atomic bomb in Hiroshima. So I greatly admired Einstein, and maybe nuclear physics can be a good physics. So I thought about doing physics in that time. And then finally I was in engineering college, chemical engineering, Department of Chemical Engineering. There, in 1965, my professor introduced 5-month lecture on physics, the Red Book. And the first edition, Asian edition, was available in the spring of '65. Then I read that book, and I was immediately attracted by this development. 5 months proposition of questions and answering that question several chapters later. And the last chapter of 5 months book was on symmetries, especially parity and CP symmetries. I didn't know very much about that. Then I thought I have to solve this problem. So basically I wanted to do physics after 1965. 5 months contributed.
So it's amazing how many people Richard Feynman brought into theoretical particle physics.
Yeah, I think so. More than Einstein, maybe.
Very good. So then you actually studied, but then you decided to move to the US, where you did your PhD, and you hold researcher positions for around 5 years. Were these years very influential for the future of your career?
Well, I was at Brown University. There I worked on some neutral current, but when I moved to University of Pennsylvania, right after moving to University of Pennsylvania, there was a Bentley Memorial Conference in October 1977. Bentley was killed 4 months ago. Then at that conference, Weinberg and Wilczek announced that the Petrarchian symmetry, which was proposed 4 months ago, of that time, contains axion. So people were trying to discover axion, and we didn't know very much about the axion. And I didn't understand. Right after the Berlin Memorial Conference, many professors from UPenn, several professors, and I discussed about this problem, and in 2 days we understood what is the problem in this axion. So many papers were written by our group. That was in 77. Actually, paper was written in 78. In 78, 79, at that period, Weinberg-Wilczek axion was not discovered, so everybody in our group were trying to obtain a solution of the problem, strong CP problem. So I think this transition period from Brown to UPenn was an important period in my life.
Fantastic. So actually, in that period, you were telling before during your talk that some of your colleagues, and including you, concentrated on finding alternatives to the axiom to solve the strong CP problem.
Still many people are doing that. That is.
And then you came with this idea of reviving the axiom.
Yeah, I tried this. So then I tried many things. I was doing well. This period was very interesting. There was the period when Weinberg finished this first 3 minutes, and we read. So we talked about this universe and also strong CP problem. And Langecker, Steve Barr, Gino Segre, Arthur Weldon, all these people did the work following these discrete symmetries and obtain small zeta bar. But I thought Petrarchan symmetry is so attractive. I always wanted to do this one. Then finally I found one. Very surprised that this coupling is proportional to 1/v. I didn't know very well, but it was very strange to me. And I get through Tony G, I sent this preprint to Wilczek, and Wilczek agreed. He didn't say directly to me, but through Tony G that it seems to be right. So that is the story of the beginning of this one. But Wilczek was not the referee of the paper, but it was somebody else.
So I think, maybe at that time you didn't realize, but certainly this changed many things in particle physics and cosmology. Nowadays, the invisible axion that has so weak couplings, 1 divided by v, right? It is one of the leading candidates for the dark matter of the universe. And many people, including here people at the University of Zaragoza, are just doing experiments to search for this particle. At that time, it was really, you realized that it was very weakly coupled, and most likely, probably, it will never be found. But still, you decided to publish the paper.
Well, decided to publish paper because it solves one important problem, strong CP problem. That was the reason. And several years later, about four years later, 3 groups gave a constraint on the on this axion decay constant, and at that time, people considered this as a constraint. And people didn't think that as a direction of new physics. I don't think in the beginning it worked only as a constraint.
Yeah, this is very,
so because
very surprising.
This is to students I mentioned. In physics or in any science, first principle, very interesting, attractive, gives some constraint or symmetry, like universe is almost the same temperature, light comes from every direction with the same temperature. But the next level you should think is that, what is the next? I mean, in the universe, if you have solved that problem, you might have obtained density perturbation. So whenever new thing comes up, first, you think, what is the next level? So you can understand what I mean. So if you find somebody propose very good thing. Then you ask, what is the next? So it belongs to this one. They give it this bound, This bound should be less than 10 to 12 GeV. FA should be 10 to 12 GeV. Then one must ask, what is the question? If it is the bound, there may be some ways to detect it. If you thought that way, you can find the mechanism. So I suggest not to think that way. If you find something, some important theory comes out here today, you ask, what is the next?
Very nice advice indeed. So I think in that sense, your proposal started a revolution on thinking about these invisible axions. You have mentioned the constraint from too much dark matter production in the universe, but then Pierre Sikivi came a couple of years later with 3 proposals to detect invisible axions, and there were some attempts, right?
Yeah.
But in the recent years, it looks like we are witnessing a new revival of the search for invisible axions and a renewed interest for model building and studying axion theories.
Yeah.
So, do you think? So, have you perceived also this new interest?
I think the trend is considering axion more these days, because at some point people thought about the so-called WIMP. A candidate WIMP might surface up from direct searches or LHC. There's some hint from LHC, but in both cases these didn't show up. So that's the reason this attraction of the axion is considered more. In any case, as a model builder, I think this one is also has to be considered, because there can be very light particles in the universe from high energy physics, string compactification. So I think both still WIMP is not discovered, but both of these has to be considered, and it is good that people consider these very light particles, not only axion but scalars.
I completely agree. Of course, I also support very much the search for other scalars in general. So I wanted to ask you about, in your career, you have studied axions, but you have studied many other extensions of the standard model, and in particular, for instance, you studied and proposed the axino, the supertwarn of the axion that could be a more massive, very, very quickly interacting particle, and could be also the dark matter of the universe.
Yeah.
So the question is, now that you are father of 2 particles that can be dark matter, so what is your opinion? Who is a better dark matter candidate, the axion or the axino?
I consider axion as one of the best candidates. Axino can depend on several choices. Axino can be heavier than gluino. Axion can be heavier than gravitino. So in supersymmetric theory, axino is introduced. So if supersymmetry is not at that low energy, axino is out, first of all. But still axion can be candidate of dark matter.
Lovely. So I wanted to close on this interview asking you 2 very general questions. So the first question is, would be, what advice would you give students that are starting now their interest in particle physics and cosmology? Do you have some advice for them?
Yeah, well, mine is too philosophical, because we, as a human being, going through this, going through all these evolutions of the cognitive evolutions about 30,000 years ago, the most important question is, where did we come from? So, even if it is not useful to everybody technology, it can be the most deep question we face. Particle physics and cosmology answers this question. What the universe is made of, if we know that, we can see the beginning of the universe. So this is purely intellectual. So if anybody who thinks to that direction, you can do particle physics. Then there can be many offshots from this thinking. If the thinking is original and creative, you can do many things which which branches from particle physics, not like people say, World Wide Web was spread from particle physics research by experimentalists and many other things, internet technology.
Indeed, motivations we have plenty.
Yeah.
And let me just then close this interview asking you one more question. So now you are actually a retired professor, but still you continue writing papers, you continue giving talks and traveling all around the world. Actually, I find you more often in conferences than to some of my young colleagues. So let me ask you a question. After 40 years or probably 50 years of doing physics already, so what makes you continue doing physics? What is your inner motivation nowadays?
Well, that is, you have to be healthy and you need some research money to continue research, to travel, to talk with the people in the front line. So in Korea, National Research Foundation support me, even though I am retired, that about $100,000 every year for next several years. So I think that kind of thing is useful to other retired professors in Europe and also in Korea. I guess then, that's the way. Our generation maybe the one of the gauge field generation, like generation of quantum mechanics. So there are many active people in our age group still who are able to continue to physics. So I think even though I am retired, our country support me to do more research. I hope this also be the case in Spain.
I hope so too. Well, Jihn, thank you very much. I hope you come back to Zaragoza and that you continue doing top-level research and looking so well.
Thank you for the invitation.